Section 6.7 is on inverse relations and functions. The inverse of a relation swaps the values of the domain with the values of the range. For example, if the ordered pair 3, -5 is an ordered pair of a relation, then -5, 3 is an ordered pair of its inverse. If both the relation and its inverse are functions, then they are called inverse functions. Let's take a look at an example here. Find the inverse of relation v, then graph v and its inverse, and we're asked, are they inverse functions? So for relation v here we have this table of ordered pairs. So if I were to graph its inverse, make a table of its inverse, for each ordered pair I would just switch the x and the y. So instead of -2, 2, I'd have 2, -2, 0, -1, 3, 0, and 0, 1. Now I need to graph each one. Relation v, I think I'll go ahead and graph that in black. So I have the ordered pairs -2, 2, -1, 0, 0, 3, whoops, that's 0, -3, 0, 3, and 1, 0. Let me change colors quickly here. And I will go ahead and graph its inverse in red. So that gives me 2, -2, 0, -1, 3, 0, and 0, 1. And here's an interesting thing about inverses is that they are actually reflections of the original function over the line y equals x. And I'll go ahead and just draw that line in here briefly. Okay, and as you can see, this point corresponds to this one over here. They're just reflected over that line, as are these two, as are these two, as are these two. Let me go back to black here. Okay, and notice that even though the original relation is a function, its inverse is not, because we actually have repeated x values of 0, and it does not pass the vertical line test. So the inverse is not a function. We have repeated values of the domain, nor does it pass the vertical line test. To find the equation for the inverse of a relation that is expressed as an equation, we want to switch x and y and then solve for y. So this says find the inverse of y equals 5x squared plus 2, graph the relation and its inverse, and are they inverse functions? So to write the inverse of y, I'm going to start by switching the x and the y values. So instead of y equals 5x squared plus 2, I'll have x equals 5y squared plus 2. Now I want to solve that for y. I'll subtract 2 on both sides, divide both sides by 5, and then take the square root of each side. So y is equal to, and when I take the square root of each side, I need to do the positive and negative. Square root of x minus 2 over 5. Now, let's go ahead and we have to graph each one of these. So to graph this, I'm going to make just a simple little table of values. If x is -1, y is 7. If x is 0, y is 2. And if x is 1, y is 7. So I have 0, 2, 1, 7, and -1, 7. So there's my original function y. And actually, let me go back over here. For some of this, let me reintroduce you to some notation you're probably familiar with. So instead of saying y, in order to distinguish this from the original function, we do what looks like an exponent of -1, but it really means the inverse. So this is the inverse of y is equal to that. Now to graph this one, I'll make a table of values. And I went ahead and did that. So when x is 2, sorry about that, when x is 2, y is equal to 0. And when x is 7, y is actually equal to either positive 1 or negative 1. And those points are going to look like this. And go out to 7, positive 1, negative 1. And that's the graph of the inverse of y. Are they inverse functions? Well, y is clearly a function because that's basically a parabola, but the inverse of y is not a function because it fails the vertical line test. So the inverse of y is not a function. Okay. Here's another example. For the function f of x equals negative 2/3 x plus 7, find its inverse. Then find the domain and range of both the original function and its inverse is the inverse of function. So clearly this is a function because that's a line, the equation of a line. It's a linear function. So let's go ahead and switch our x and y. Remember, I can think of f of x as equaling y. So that switching x and y gives me x equals negative 2/3 y plus 7. And now let's solve for y. So I'll subtract 7 on both sides. And then multiply both sides by the reciprocal of negative 2/3. So that'd be negative 3/2 times x minus 7 is equal to y. And I'll go ahead and put that back into function notation. So I can also do the negative 1 for this. So it looks like f negative 1x. We read that as the inverse of f of x is equal to negative 3/2x plus 21/2. I went ahead and distributed that. So there's my inverse. So that is also the equation of a line. So because both f of x and the inverse of f of x are linear functions, both are functions. So the inverse is a function, and because they are equations of lines, both the domain and the range are all real numbers. Okay, this is a little confusing. So this says if f and the inverse of f are inverse functions, then f of the inverse of f of x is equal to x, and the inverse of f of x is equal to x. That's the notation your textbook uses. I find that a little confusing. Let me show you another notation that I'm more familiar with. Instead of calling the functions f and the inverse of f with a little negative 1, let's call them f and g. So if if f of g of x is equal to x and g of f of x is equal to x, then we can say that f of x and g of x are inverse functions. In other words, if you do the composition of functions doing f of g and then you do it with g of f, and when you simplify that out, they both equal x, then we know that the functions are inverses of each other. So let's take a look at an example here. So we have f of x is equal to 3/2 minus x, and we need to find its inverse, and then we need to find the composition plugging in 2 for x. So let's start with finding the inverse. So let's go ahead and switch x and y. So I have x equals 3/2 minus y, and I need to get y by itself. The problem is it's in the denominator. So if I multiply both sides of the equation by 2 minus y, and then I'll divide both sides by x, I get 2 minus y is equal to 3/x, and then subtracting 2 on both sides, negative y is equal to 3/x minus 2. Let me pop it up here. Dividing everything by, either dividing or multiplying everything by a negative 1 will give me the inverse of x is equal to negative 3/x plus 2. So there's my inverse. Okay. Now I need to find f of the inverse of f of 2. So to do that, I'm going to rewrite it a little bit here so it makes a little more sense to me. So I need to find f of the inverse of f of 2. So I'm going to take 2 and put it into the inverse function here. So I'm going to need f of negative 3 over 2, putting in 2 there, plus 2. Simplifying that, f of negative 3 over 2 plus 2 is a positive 1/2. And now I'm going to put 1/2 into my original function for x here, f here. So 3 over 2 minus 1/2 is 3 over 3/2, and that is equal to 2. So the composition of f of its inverse of 2 is equal to 2, which is kind of cool. Let's try it the other way. Now I need to find the inverse of f, and then I'm going to do f of 2. So the first thing I'm going to do is put 2, oops, I kind of lost it there. I'm going to put 2 for x into f right here. So when I put 2 in there, I'm going to end up with 2 minus 2 on the bottom. So that gives me 3 over 0, which is a problem. I can't do that. That's undefined because I can't have 0 in the denominator. Okay, so what that means is that the composition of the inverse of f and f of 2 does not exist because I ended up with a 0 in the denominator when I did that. So in this section we took a look at inverse relations and functions, the fact that the inverse of a relation basically just swaps the x and the y. Sometimes the original can be a function but its inverse is not, and then we looked at how to use composition of functions to determine whether things are inverses or not.